Okay. I'm very glad to be here to give a talk. I hope you are all safe in good places. And I'm going to talk about the beginnings of gravitational wave astronomy, which was a field that started in about 2015 with the first detection of a pair of black holes that collided with each other, but not through light or not through radio waves, but by gravitational waves. That's how we actually detected it. And so this is the story, a little bit about the technology and also the directions in which this field will go in the future. So let me start by acknowledging the people who actually worked on this thing. Oh dear, something is not functioning. Here we go. Yeah, this is a group of people of about 1,000 people at about 100 institutions all over the world. And this is their logo of people who've worked on LIGO. And many have done work on the apparatus. Some have worked on data analysis. And a lot of people have done was very profound work on making this is a group venture, not of single individuals, but of a large group of people who made this happen. So let's start with what a gravitational wave is and what it isn't. Here is Isaac Newton, who did a very profound thing in science. What he did is by combining something which is going on in the heavens, in other words, using planetary motion, which others had measured, and knowing a little bit about what gravity felt like on the Earth, he made a theory that combined the gravitation that went on in the heavens as well as with that which went on the Earth and made it into a single theory. That was unheard of. There was never such a thing before, at least in science. And the thing was embodied primarily in a very simple equation that there was a gravitational force. That gravitational force had a constant that depended on the units. I'm not going to bother with that. But the important thing is it depended on the strength of the gravitational force, depended on the mass of one object, let's say the sending object, and then the receiving object. And it got smaller as the square of the distance. And we use this to do almost everything with gravity. When people send spacecraft into the moon or they send them out in the ocean, this formula is almost all you really need to predict almost everything that happens. But there's a problem with the formula, which is it doesn't really work for masses that are moving very fast. That's a development that came many, many years later. And it doesn't really explain how things communicate in a gravitational field. And that is the basis of gravitational waves. In other words, how information travels from one place in a gravitational field to another. Many people, when they apply Newton's theory, assumes that, and I know they all feel very strange about this, but they assume that if you make a sudden change in a gravitational situation, the influence of that propagates away from the place where it happened with an infinite speed. That can't be true because after Einstein, we know that nothing that carries information or energy or anything that carries true information can move faster than the speed of light. So those are in the end going to have to be attributed to gravitational waves. So here then is the beginning of something wrong with Newton's theory, but it's a very, very tiny little effect. It doesn't matter a lot. And you will see it's also quite hard to measure these things. So here we go. Here then is Einstein. And Einstein has replaced Newton's equation with something very much which looks deceptively simple, but is enormously complicated. This equation here relates the way space and time is measured. Space and time is measured. That's G. It relates it to how energy and mass, but energy is distributed in that space. So there's now a relationship between what space actually looks like, whether it's Euclidean and how the time of clocks run, and all of that is related to how you distribute matter and energy in the space in which they've been put. And now let me give you a little feel for what that equation does. It's very hard to solve that equation. And people have you will see a solution to that equation that has been made by computers only in the recent years. But the very early equations, there were early equations of the solutions of the Einstein equations, but they were always for very, very simple systems. And now we can do more complicated things because a computer can, if you program it properly, can solve these equations. So let me give you a little feel of what I meant by what Einstein's equations mean. And what this is, imagine a jungle gym, a place where kids play in, children play in which you have all sorts of parallel bars. In many playgrounds in New York City, you'll find if you come to New York, you'll see kids playing in a three-dimensional thing that looks like this bunch of bars down here. And if you lay it out here, the bars are all equally spaced. And if you put clocks here, I haven't put the clocks in, but if you put clocks at each intersection of these bars, you will find that the clocks keep the same time at the same moment of time. So out here where this looks like flat space, it's a cut through a jungle gym. It's a cut through the jungle gym, a two-dimensional cut. Now I put the sun in here. The sun is a very strong source of gravitational field. And what it does is it distorts the space. It curves the space. So now particles don't travel along straight lines like this anymore. They will follow lines that are more curved. And this curvature of space, and by the way, a change in the way time is kept, that the clocks that would have been out here, the clocks that are here and there and there and there, they run more slowly than the clocks that are out here. And that's a very important effect. It's called the time dilation effect. It was one of Einstein's very first predictions for his theory, but the spatial curvature was another. And so you can see here's the Earth, and it does the same thing. It's not as powerful as the sun. It makes a little curvature of its own, and it makes clocks go a little more slowly in its vicinity than out here. And that's the image I want you to carry when you think of Einstein's theory. What happens now is that this space and the way the clocks have been changed cause this body, which is the Earth, to move around the sun in an orbit that you can calculate by using Newton, but it's a deeper understanding of what is going on if you use Einstein's theory. Now, in Einstein's theory, there are gravitational waves. And what they are, and then Einstein made some mistakes, always interesting mistakes. Every mistake Einstein made is always interesting to understand. He was wrong. He wrote two papers, one in 1916 when he did what's called perturbation theory of his theory. In other words, looked at cases that were not very strong gravity. And he made a mistake there. And then he wrote it all over again, a paper only on gravitational waves in 1918. These papers, by the way, are now translated and they are on the web, so you can read them. This is what Einstein assumed. Einstein showed that the sources of gravitational waves are non-spherically symmetric accelerated masses. In other words, it's not so different than electricity and magnetism. In electricity and magnetism, the source of electromagnetic radiation are accelerated charges. But here it's masses that are accelerated, but it's not all motions of mass. It has to be non-spherically symmetric. For example, two objects that are smashing into each other, they will radiate gravitational waves. Or two objects that are going around each other, they will radiate gravitational waves. But an object that expands and contracts uniformly will not radiate gravitational waves. And that's the mistake Einstein made in 1916. He assumed they did, but it changes nothing. It turns out this is a very important part of detecting gravitational waves. These have to be non-spherical motions at the source, but they have to be accelerated mass. Now, the kinematics is something Einstein guessed at. He guessed that the propagation velocity, the speed of propagation of gravitational waves is the same as light. In other words, the speed of light. And he also assumed and showed in his very first paper, he showed this, that they were transverse waves. And I'll show you that in this picture in a minute. The waves, if they travel, let's say in the Z direction, they cause stretching and compression in space in the X and Y direction. So now I want to explain this picture a little better. This is a picture of let's suppose you put dots all over space. And here's the place where you're standing. You can see a little red square right there. And I'm now going to set the gravitational wave moving. In other words, you will see these dots move. I hope you will. Yes, oh, wonderful. The animation worked. So now if you look at this for a little bit without going too dizzy, you will notice that there is two motions going on. In the up and down direction, there may be stretching of space, but while in the horizontal direction, there is compression of space, and that keeps flipping back and forth. I hope you can see that. There's expansion in the X direction while there's compression in the Y direction, and then that inverts. So that's one thing to keep in mind when you think of how you make a detection of a gravitational wave. The other thing that you should keep in mind is when you stand near you, right near you, the two masses that are close to you, they're moving a little bit. But the ones that are furthest from you, like this one and that one, they are moving a lot. And that is a motion of constant strain. If you stop the picture, it's the same as you have taken a rubber band. If you take a rubber band and stretch it a little bit, and you let a friend of yours make marks every centimeter on that rubber band, and then you start pulling on the rubber band like this, pull it apart, you will notice a motion that's very much like what's going on in either the X or Y direction, depending on what's going on, it's shrinking or not. That is a strain that's induced by a stress in the rubber. And that's what's going on in space. So if you want to detect gravitational waves, you can now see what you might want to do. You would put objects as far apart as you can, and you would look for both motions in X and motions in Y, both of them perpendicular to the direction in which the gravitational wave moves. Okay? And the first person to try this was a fellow at the University of Maryland in the United States named Joseph Weber. The way he did it, here he is. You can see it here. He's putting what's called strain gauges on a big piece of aluminum. It's a very large piece of aluminum, bigger than he is. And what he's hoping is a gravitational wave will come along and stretch the aluminum this way and compress it. Let's say stretch it along its longitudinal dimension and compress it along its transverse dimension. But you won't measure that. What he's really looking at is the stretching along the longitudinal dimension by having glued these little strain meters to that bar. And he takes that bar and puts it inside this vacuum system and closes the gate on it, closes there's a door that gets put on there, and tries to keep this from being excited by noise in the room. And he had a very unfortunate experience, Mr. Weber. He had one of these in his university in Maryland, University of Maryland, a state in the United States. He had another one in a golf course, a place where you play golf near the university. So they were about 8 kilometers apart. And then he had another one in the city of Chicago, which is in the middle of the United States. And he was hoping to see this, and he did see it. And that was his misfortune. He saw that there was typically a stretching of these 3 different bars in different locations at about the same time, 2 or 3 times a day. And he got very, very excited by this. And after watching this for a while, he published a paper in 1969 saying that he had discovered gravitational waves. Well, the nice thing about science is that if an experiment isn't too expensive or too difficult to do, other people can do the experiment also. Now, this is a moderately big experiment, but it isn't all that expensive. And a lot of people in Russia, there were at least 2 groups. Russia in this case was in Moscow. There was a very famous man in Moscow named Vladimir Braginsky, who actually worked on this thing very much later than Weber even, and he kept trying to improve these. But none of them saw what Weber saw. All over the world, people were doing this experiment, and they did not see anything, including Braginsky in Moscow. And that is the way science is done. if somebody makes a statement, then you can check it if it's an experiment. And if you see it, then you have confirmed the discovery. But if you don't see it and you really understand that you don't see it, you can refute the experiment. And Weber was not very kind to people who refuted his experiment. He was, in fact, very upset by this. But later on, it turned out that he started a field which did work. And here is the way it ultimately did work. And this is a little mock-up using what's called interferometry. This is what this is. It's a little interferometer. And what is done is and this will be a little animation in a minute, but this is a laser. It doesn't look like a laser, but the laser will send out a light beam. It'll go to this beam splitter where half the light gets transmitted and the other half the light gets reflected. And then it goes to a mirror here, and it goes to a mirror there, comes back from both of the mirrors, and then goes to a detector. And you'll see what happens now when I start this experiment. So wherever you see red, there is laser intensity. And the wiggling thing you see are the electric fields that are in the light beams. And you can see them coming back to the beam splitter. And now, if you look to the detector, you'll see that the light beams have canceled each other, because this path and that path are identical in distance, and the electric fields have the opposite sign. So no light goes to the photodetector. But now you move these mirrors, move one closer and the other away, and not be equal distance. You do see light at the photodetector. So that's the way you make that's how you make the detection. You have a photodetector, a laser, and you have these mirrors which are moving oppositely directed. One is going away from the beam splitter, another's coming toward it, and then that flips. And they're changing the equality of the paths between the beam splitter and the mirror. And that is, in fact, the basis of the entire detection. It gets very much more complicated, as we'll see in a minute, but there is no more invention needed. That is the basis of the detector, right? And all you need to think of is that little picture with the dots and who moves which way in the picture with the dots that I showed you before this. And then you have the whole idea of how the gravitational wave detector works. The problem was given by Kip Thorne. Kip Thorne is a very famous physicist. He happens to be at the California Institute of Technology. He has spent, by the way, Kip has spent time in both Ukraine and in Moscow. And he brought Vladimir Braginsky to the United States for visits. And Vladimir Braginsky and he came up with a lot of the things that I'm about to tell you. What Kip, who knows some astrophysics, said, look, this strain, which is the change in length between dots on that picture divided by their separation. So that's a change in length divided by a length. And we give that a symbol called H. If you're going to try to detect gravitational waves, you're going to have to make a detector that can measure smaller than a strain of 10 to the minus 21. And that is very, very hard. And the reason is it's very hard to distort space. A gravitational wave has to carry an enormous amount of energy to distort space. And so, and you don't have that much energy available all the time. So if you want to see a gravitational wave, you have to make a very sensitive device. And for example, if you make the path length difference between the beam splitter and the mirror 4 kilometers, the change in length that you have to measure is 4 times 10 to the minus 18 meters. What that is, it's about 1,000th the size of a nucleus. And that was turned we had to work on this technology for about 35 years before we got it to the point where we actually were able to get to a sensitivity like this. And what was the big challenge? The big challenge is with a strain of that small or a displacement that small, you would have to measure 10 to the minus 12 of a wavelength of light. What we use is infrared light, which has a wavelength of 1 micron. But that was hard, but we accomplished that fairly quickly. The thing that was much harder than that was to make sure that the mirrors and the beam splitter, but mostly the mirrors, the 2 end mirrors, did not themselves move by more than 10 to the minus 12 of the vibration of the Earth. And the Earth is jiggling everywhere, wherever you are. It's jiggling at least by a few microns, a few times 10 to the minus 6. And you have to go a factor of 10 to the 12 in reducing the Earth motion to be able to get down to this motion. And that's why this turned out to be really difficult. Okay, so that's the place why it was such a triumph to be able to detect gravitational waves. The idea is straightforward and simple. Doing it was just difficult. And here is the actual detector that is the layout of a real detector that does this. And I'll give you some of the tricks that were done, that were done. So here you already know some things. Here's the laser, and here's the beam splitter. You saw that in the little mock-up. And then here's a distant mirror, and there's the other distant mirror, and there's the photodetector. Now there's some new things in this picture. The first new thing is that there's a second partial mirror in here. And what that does is it takes the light and transmits some of it, and it causes the light to bounce back and forth 300 times. So the light is spending 300 times longer in the gravitational wave that's coming from above. Or another way to think about it, it's 300 times longer than one arm, which is 4 kilometers. And you make this identical to that. So the time spent in this arm and the time spent in that arm are the same, and no light goes to the photodetector. Now, if no light goes to the photodetector, then all the light that comes out of the laser hits this and comes, well, what it does is it comes back again. And there was a very clever idea had. You put another partial mirror here, a mirror which transmits part of the light, you do the following trick. You put this partial mirror here so that when you take the laser light and reflect it, there's a reflection from it, and combine that with the transmission of the light from the beam splitter, the two cancel each other interferometrically. So no light gets back to the laser. The laser does not like to operate with reflected light. So this is called a power recycling mirror. And what it does is that you might have a 10-watt laser here, and with a 10-watt laser and no light coming back to the laser, and the light builds up in this cavity. There's a cavity which has this mirror as one mirror, that mirror as a second, and that one as a third. And here's the beam splitter. And the light in here, instead of being 10 watts coming out of here, it might be 500-600 watts in these 3 arms. So then in here, it might be a megawatt of light. And that is ultimately the trick that was necessary to get the light power high enough so that you could break a fringe down into 10 to the 12 parts. But that's the trick for how to solve the optics. This mirror I didn't talk about, but it was used in the same detector that was ultimately made the detection. In the earlier detector, we didn't have this mirror. And what it does is it allows you to change the spectral response of the instrument. I'm not going to talk about that, but you're welcome to look that up in the papers. It's called a signal recycling mirror. What it does is it reflects the sidebands. To those of you who care, it reflects the sidebands that are generated by the gravitational wave in these arms and reflects them back into the interferometer. And you can then tailor the spectral response of the system. Okay, so here's how one of these systems works. Those mirrors are supported by pendula. These mirrors. Oh my God, no. Yeah, let me go back. Yeah, these are all, wherever you see this and you see a thread, this is a pendulum. All these mirrors are not sitting firmly on a table. They're supported by a pendula. So that's how you isolate yourself from the ground motion. And so here you see the amount of noise, and this is in units of the strain per bandwidth, square root of bandwidth. Okay, the detection bandwidth. And for example, 10 to the minus 21, here is strain per square root of bandwidth is equal to about 10 to the minus 23 on this line. Here is 100 hertz. And so right about in here, it's about, you have a sensitivity of about 10 to the minus 22 root mean square sensitivity. It's about 10 times better than what Kip predicted was needed. And so here is these are the different noises. This is the quantum noise in the system. Here is the fact that you're having discrete photons in the interferometer, and you have phase noise from that. The phase, the actual detection noise of comes in. And here is the other half of that. This behaves like a big giant Heisenberg microscope, this instrument. And this is the radiation pressure fluctuations due to all those photons on those end masses, and they're pushing the mirrors around. So you get noise as you increase the laser power, you push this noise down. You can measure the phase of the electromagnetic field better and better, but you make this worse and worse because there's more and more photons hitting. It's like a hail of rain of photons on the mirrors. So this is the quantum noise in the very first detector we made. This is the thermal noise in the suspensions, the fact that we're operating at room temperature. And there's a little bit of that in the fibers. There's a little of that in the masses themselves. And then those are the three big noises: the quantum noise, the thermal noise, and the instrument noise, the residual gas that gets scattered, but you can pump that out. And we got our system way down to here by pumping those big long tubes down. The noise you can't get rid of is this noise right here. And what is that? Oh, there are two noises here that you have trouble with. This one is the remaining noise from the ground. It's called seismic noise. And that is when you when you build a car and you try to make the car so it doesn't get hit every time you get a bump in the road, you use a mass and a spring system to isolate the car and you as a passenger. The same thing happens here. You can isolate the mirror by making better and better masses and springs. And that we did in the initial interferometry, we did about as well as we could. And that was one boundary. And then the other one is this one, which is a different kind of noise. It's the noise in the fact that even though you might have made yourself a very good isolation system, you still can't get around the gravitational interaction, the Newtonian gravitational interaction between the fluctuating density of the ground and the mirrors. The fluctuating density in the ground is making ordinary Newtonian forces, and these pull on the mass, and also fluctuations in the atmosphere, the density in the atmosphere. And this very rapidly gets worse and worse at a very, very fast clip, and makes it so that you really can't do very much with on the ground for gravitational waves much below one hertz. And that's why people go into space, and that's going to happen. You'll hear that at the end of the talk. Okay, so this is a typical layout for an initial detector. And here's a little bit about the detectors. There were two in the United States, one in southern United States, another one in northwest United States. There was another one in Italy, which was finished later. There's a shorter detector in Germany, and built very recently was a detector. These are detectors that were not part of the initial experiment so much, but in Japan, there is a long 3-kilometer detector, and there is being built in India at this moment a 4-kilometer detector. And these are why you want so many detectors is to do astronomy. You need that to be able to identify where the sources that you have are on the sky. And then other people with other kinds of instruments can look for this source. So here's a little tour of, this is the source. This is the detector in south of the United States. This is the detector north. This is sort of what looks like. Big tube is inside this. This is a piece of concrete. This is the same tube in concrete in the southern United States. Here's a vacuum system to which the laser light has to be traveled. And this is a laser instrumentation table, like many of you may have had in a laboratory. And this is the control room in Livingston, Louisiana. And here are people learning how to operate the detector. So it's a moderately big experiment. Okay. And here's how well we did. And this is now in a different units, but don't let that scare you. This is in displacement. It's how much motion. This is meters per square root of bandwidth. And it starts way up here at 10 to the minus 11 meters, and down here at 10 to the minus 19. Huge range. And this is frequency. So this is 10 hertz, 100 hertz, and 1,000 hertz. And when we started, this is sort of just a history. when we started the instrument back in 2001, this is the noise curve we had. And it got better and better and better and better and better. And eventually we got down to here in about 2005. And you can see that the noise curve sits on top of a dashed curve, which is a theoretical noise curve. And it doesn't quite make it at low frequencies, but above about 80 Hertz, the experimental curve is right on top of the theoretical curve. And we felt very proud of ourselves that we had gotten to that point. It was unfortunate that the instrument wasn't good enough yet at low frequencies, but we had what I would call a clean non-detection. We could tell people there were no gravitational waves at a level that would have caused the motion of these masses by 10 to the minus 19 meters at frequencies above about 100 Hertz. So because we were successful at this, the United States government and other governments, in this case, the British and German governments, helped by putting some money into this experiment and to make it a second, what's called a advanced detector. And here's what was changed. The things that were changed were the things that would change the noise at low frequencies. And so here, for example, we made a much more elegant suspension. For example, you can see springs, and here's a first pendulum. This spring is attached to the ground. And here is the first pendulum. Then there's a second pendulum hanging from this first, so that's the second pendulum. Then there's a mirror that isn't really used as a mirror, but that's another mass that's like a mirror hanging. And finally, there's a fourth. There are 4 separate pendula, all hanging from each other. And each pendulum gives you an isolation of 1 over frequency squared, about, when you're above the resonant frequency of the pendulum. And this then, that whole system was mounted on something even more complicated. There it is. There's the 4 pendula together. And that was mounted on a thing which many of you might be able to use. The idea is a good idea. What you do is you make a platform which has an inertial sensor, like an accelerometer or a seismometer on it, and it is pushed around relative to an outer system. And what you do is you push it in such a way that it's in a feedback loop, so that the accelerometer or seismometer is nulled. In other words, the motion of the seismometer is brought to 0 by the negative feedback system. And that's done twice here. There's an outer system and an inner system. So there are 2 what's called active vibration isolation systems here. And they then support this very delicate system, which is a passive system. And then the noise looks a little different now. I won't go through this, but this is the noise curve. You can see, well, I'll say a little bit about here, the quantum noise dominates. There's the quantum noise. And now, and here is the thermal noise, that blue one. And then there is that gravity gradient noise, which is the one that is getting very close to being dominant here at low frequencies. And then we have a new noise, which we hadn't even thought about. That's this thermal noise right here, the red line, thermal noise in the coatings of the mirrors themselves. And that is, we're still fighting that. And so that was the detector called the Advanced Detector. And this is what we saw in 2015 when we ran that. And what you see here is a signal. This is the one, and Livingston is the southern, and Hanford is the northwest detector. And here is the scale. This is in strain, and it goes in units of 10 to the minus 21 strain. And here is the time. And you can see this whole thing is only about 1/10 of a second from here to there. And this is junk, this is noise. And then it's noise again out here. But in here, there's something coherent. And then you look at Livingston, at Hanford rather, and you see this is noise again out here, same noise, but this is almost the same as that. In fact, you can put them on top of each other. And they're not identical because there's noise in the instrument, but that signal was very important to us, that the signals were very much the same, 2 detectors. If we had that, we didn't have that, we would not have been able to publish this as a detection. That was a very important feature. And it was also an important feature to Weber, when I told you about him earlier. Now, this is a spectrum. And it's the same data, nothing new here. This is now, instead of this being a displacement, it is the spectrum of the motion. In other words, the frequencies that you would include in a Fourier transformation of that time series, which is this one. But now, for example, here is the middle of middle C on a piano. Okay, 256 hertz. And here is the sound. And where it's bright, you have a lot of that frequency. So there's a lot of 256, not so much lower frequencies. And now if you turn up your sound a little bit, you might hear something. That roar, I don't know how many of you were able to hear that, but that roar was a signal to people at the operation room heard. In the morning at 4 in the morning, only 2 people in the whole world heard that. And this is the same thing changed. In other words, what we did here is we tricked it up, so we changed the frequency of it. And a chirp, chirp, shoop, whoop, like that. And that was the big deal. That was the big discovery. And what was it? Well, I have to say a little bit further. The important thing that has happened in the field by the time, this is about 2015, people who had been working on computer solutions of the Einstein equations, those equations I showed you in the second slide or third slide, had succeeded, finally. It took them very, very long time because it's very hard. They're very narrow equations. And they had worked for years on trying to make a black hole pair, a binary black hole collision. And this is what after modeling, this picture is the computer output. It's not a drawing by an artist. It's the computer output of the curvature of space and time of a pair of black holes weighing about, well, we'll get to that. It's close to 30, something close to 30 solar masses. And let me get this going, and you'll see then this is the best we can do right now to visualize what that event was all about. So you see the 2 black holes, they're going to go around, and here the time is here of the collision. Time series is down here. So now what you notice is that here are the black holes, and these are the black holes. The light is where it's green, time is pretty straight, but once it turns orange and black, the time has dramatically changed. And you'll see the clocks of, and those arrows in this thing are the strain in the space. And you'll see as they get closer and you look closer, they're losing energy to gravitational. It's slowly going around. Eventually they'll slow this down a lot. Now they've slowed the time down a lot. And you can see how the curvature is increasing dramatically as these 2 black holes get closer and closer. By the way, they're going very close to the speed of, about 0.6 the speed of light. And now they've collided, and you can see time has stopped inside the new black hole. And that now relaxes, and you can see the gravitational waves leaving the black hole. And this is the best explanation we have. What we saw, it matches, and let me wait for it to stop. It matches, well, I think, let me come, if you can ask me about this. This is just a joke, but let me go on. This is what we saw on, this is a little, you have to know the notation a little bit. This is the gravitational wave we saw in the year 2015, in the 9th month on the 14th day. And this is the thing we just saw the computer solution for, but that's the actual data. And well, many of us, you can solve for it. It turned out that that thing had 36 solar masses for one black hole, 29 solar masses for the other black hole, and 3 solar masses went away as gravitational waves. I'd like to say something about this collision and this gives you a little feeling for how tiny the effects are that gravitational waves make with this huge expanse of energy. For example, had this happened at the position of the sun, suppose the 2 black holes had been at the sun, the value of the strain we would have measured on the Earth, you would have felt that your head was a little shorter than your feet, toward the feet than it was around the tummy. In other words, you would have had a strain of 10 to the minus 6, 1 micron, maybe half a micron. You could never measure it. I mean, it's, unless you had a really interferometer, but the amount of power that was going through you, this is the watts per meter squared that was going through you of gravitational field energy is 10 to the 25 watts per meter squared. Now, when you get a sunburn from the sun and you're in the, let's say you're in the open, you have 1 kilowatt, 10 to the 3 watts per meter squared. This is 10 to the 22 times more energy than the sun is putting out as light to you. It's an unbelievable amount of energy, but it makes only this infinitesimal effect. It tells you that space is extremely hard to distort. It's stiffer than steel by a factor of 10 to the 20 at 100 hertz. So that tells you why it's hard to see these things, even though they carry remarkable amounts of energy. Well, we thought we saw another event. It's not made into a GW. We weren't sure of it on October 12th. And there it is. It's much smaller. These are the units. These are the parameters for it. Then we saw this the day after Christmas. This was extremely convincing. We saw this. We saw it for a long, long time. And this was 14 solar masses with 7.5 solar masses, 1 solar mass going off in energy as gravitational waves. But once seeing that, a lot of us began to think, aha, maybe this was real, because this looked like you could almost do this one without using the Einstein equations. That's a small enough velocities. And then lo and behold, this is much later, a year later, and then we saw more and more and more of these. And so that started the field. This is the start of the field. We didn't have the courage to publish it until we saw this, because it was a new apparatus. We didn't know much about it. We were very worried about making a mistake that was like Weber. It's a mistake after all that effort, but we made a judgment that was right in the end. So then here's what's happened since. One of the most important things that's happened since is there was the new detector Virgo came on the air. This is in 1708, August of 14th day of August of 2017. Here you can see it's not a wonderful detection, but this is the south. This is the Pacific Northwest. This is the detection was a little better in the south, the LIGO detection. But now Virgo was on the air. The Italian detector was on the air, and they saw something, and there it is. So it was finally another detector in another place could see where it is, and that made a very big difference. Not only did it give everybody in the world more confidence that we weren't making a mistake, or the world was not making a mistake in believing us, but here's what it actually did for astronomy. This is a picture of the sky. And if you use only the LIGO detectors, these two, the uncertainty in the position on the sky would be this shape right there. It's about 1,000 square degrees. But adding Virgo to it reduces the uncertainty to about maybe 30 square degrees. Okay, and now you could tell somebody a little better where this was. Now, all the sources so far we've seen are billions of light years away, 10 to the 9 light years away. So it's not so easy to tell somebody exactly, even though, but you can tell an astronomer where things are, then they will at least try to look. And every astronomer has done this ever since we've detected now black holes. They have immediately gone and tried their best to make a detection of the thing with an optical telescope. So here then is the next thing. Now, here's sort of, this is the history is about half a year old. Here are all the binary black holes we've seen here, their masses. Here are the electromagnetic neutron stars that have been discovered. And some of these black holes here are black holes that had been discovered by X-ray astronomers. All the ones with pairs are ones we've discovered. So we have about 100 of them now. And people are learning a lot about it. But the most interesting event that happened after this, it was already extremely interesting to see a pair of black holes. I mean, people were never sure of black holes, and we'll get to meanings of that in a minute. But the thing that was a real eye-opener for everybody was this event. Now that you know a little bit about the field, let me show you what it is. It's an event that has a very much longer chirp. You can see it. This is the power spectrum of the strain, and it goes on a long time until it gets down to here, and then it gets off our sensitivity curve. And let me play it for you. It'll take a while for you to hear this. It starts very low frequency. okay? And this is that whoop at the end. And now here is that fantastic thing that happened. It was seen as well by the Fermi satellite as a gamma ray explosion. Here is the end point of our chirp when the two, and we believe what it is, as we'll see in a minute, the two stars, and they are not black holes in this case, they're most likely neutron stars. Those are stars that are the size of a city with the mass of the sun. So they have an enormous density. They have a density of nuclear matter, sort of 10 to the 13, 10 to the 14 grams per centimeter cube. And they collide, and they're made mostly of neutrons. And what they see here is this gamma rays, they see nothing. Here's the moment when it happened. About 2 seconds later, or 1.7 seconds, they see a gamma ray burst at between 10 and 50 keV. They look at another channel, they see it between 50 and 300 keV. And here is another satellite called the Integral satellite, which also saw it. But the important number that to us is the following, and this is the one that made it so that we now know exactly that gravitational waves travel at the velocity of light as Einstein guessed. There's no question about it anymore. This source is about 160 million light years away from the Earth. We know that from people having identified it, as we'll get to in a minute. And now we get the gravitational wave and the electromagnetic wave, which makes the gamma ray bursts, have been traveling together for 160 million years. And the biggest space they have between them in time is 1.7 seconds. You do the arithmetic for that and you find out that they travel at the same velocity by a part in 10 to the 15, 10 to the minus 1, 5, 10 to the power minus 1, 5. So they traveled the velocity of light to an unbelievable equality. So here's what people think this was, and this is where the fact that Virgo was on the air was so important. Because here now is the picture of the sky again. And here then are the bananas of the uncertainty. LIGO had an uncertainty that was this big and also had an uncertainty for complicated reasons here. 2 bananas. If you now take the Fermi lab, the Fermi satellite, it doesn't have much angular resolution. So its uncertainty is bigger really than the LIGO one even, except for this 2 element thing. But now if you take Virgo and add it to it, and oddly enough, Virgo didn't see it, but you could infer that they should have seen it, which meant that it was in a very special place in the antenna pattern of the detector, a place where the detector is insensitive. That's a cone. That's 45 degrees to from the vertical or horizontal. It turns out you're insensitive to one polarization of gravitational waves there. And that's what was going on. And so we used that and found out and this is astronomers, within about 10 hours after this, they had the data and they saw this galaxy, NGC 4493, here it is. And here are stars in our own galaxy, these guys, but they saw this extra near bright thing, which wasn't there 20 days before. This is the same galaxy. 20 days before, there was nothing at that point. So that is the neutron star explosion, the collision of the 2 neutron stars. And all of this is only possible because of, the Virgo detector had been proved to be sensitive and was on the air. So that's what we mean by having multiple detectors. You could do a lot more science. And here's some of the interesting science that came out of this very shortly after. First is, what was it? Well, we now know for sure that it was a black hole pair that went in, a neutron star pair that went into becoming a black hole. And then this, the neutron material spread out into space all around us and made something called a kilonova, which was followed for almost a month. It's still being followed, but the important part for a month after the collision, and people saw the light curve, and they were able to infer a lot from the light curve. And the radio astronomers were able to see a radio pulse from the formation of the black hole, and they saw this gamma ray burst and also a radio pulse from it. So almost every form of astronomy saw this. And here, for example, is one of the important results from this. This is completely out and nothing to do with gravitational waves. What it is by looking at the light curves that followed, you could tell that here's the periodic table. Many of you will recognize. Here's hydrogen and here's helium. And it's always been an interesting puzzle where different elements came from in the history of the universe. And there's a color coding here where if it's blue, it came from the universe explosion itself. And if it's orange and green like that, it comes from the inside of stars. Stars are very good furnaces for making heavier elements, but they're not very good for making very heavy elements. You need to have a lot of neutrons around. And it's always been a mystery where all the purple ones were made. Now, people had guessed that neutron stars were the place where heavy elements were made. And for example, gold and platinum are a result of neutron star collisions, just like the thing we saw. Now, the people didn't see the actual lines, but this comes from modeling. And it's 95% convincing to people. The 5% is there's still people holding out that you could have, it's a very low probability that it's all stars, but it's very unlikely. Namely, they now think, and almost everybody in the world thinks, that all the heavy elements were made in neutron star collisions. So that was an interesting result. Whoops, I didn't mean to do that. Here's another result, which is a little more difficult to explain. And I don't have much time anymore. I have about 4 minutes. But what it is there's been a controversy about the Hubble constant. This is now for specialists in the audience, that by measuring by measuring supernova in distant galaxies, people can get, knowing supernova in our own galaxy and the neighboring galaxies, you can get the amount of brightness that a supernova has. That gets you, if you know the distance, that gets you the Hubble constant, which tells you what's the velocity. There's a redshift there's a Doppler shift of all the lines, the spectral lines in a star that went into a supernova. And that's due to the fact that the further the star is away from the Earth, the faster it's moving away from the Earth. And this has always been a basis for evidence of the initial cosmic explosion. It's one of the best evidences we have. And it's the relationship between velocity of recession away from the Earth related to the distance that the object is away from the Earth. That is the Hubble constant. And that has been seen by people doing supernova searches at now values that are centered around 72 or so in these funny units, kilometers per second per megaparsec. That megaparsec is, parsec is about 3 light years. So this is 3 million light years. That number has been varying all over the place, but it's getting smaller and smaller, the uncertainty. Now, it turns out you can do the same number by using the cosmic background radiation, which is the 3-degree background radiation, and mapping the anisotropy. And that gives you a Hubble constant in a different way, which is more a more cosmological way rather than a near field way. And they don't agree anymore. Now, as far as I'm concerned, they agree pretty well. But people are making a big fuss that the data is so good that they believe this is really a gap. I mean, I've lived long enough to see this constant vary by factors of 2. So I'll hold judgment. But if you do it with LIGO, you can use LIGO as a way of doing it too. You can use the fact that you can measure the neutron star mass by looking at the waveform that's generated in the gravitational wave. And if you know where the thing is, if it's in a galaxy, you can measure the redshift for, you can get another way of getting the Hubble constant. And here is for one example, a probability curve for what's the Hubble constant using one example of that neutron star measurement, where you use the fact that you know the sensitivity of the detector and you believe the Einstein equations to get you the mass. So that's a field that's going to mushroom as soon as we get more and more of these. We will use gravitational waves to do cosmology. Another thing which is going to be shown is that, and let me go back one, is that there is something which you could get, which we haven't yet. That's going to be information we get to these 2 neutron stars. Here's the actual curve for their oscillation as they go around. In other words, this is the this is the period of oscillation of the two neutron stars around each other. And they will change that period. It won't be just gravity from gravitational waves. There'll be a distortion of the star. You'll notice a little bit of it. This star pulling on the mass of the other star, causing a tidal term in the star. And that tidal term will cause the period of the star to vary. And we're looking for that. We haven't found it yet, but that would be absolutely incredible. That'll tell us what is the equation of state of nuclear matter. That's something, and you will get that another way by looking with people trying to look for that too. Oscillations of the neutron material as gravitational wave signals. And these are some models for that. This is all in the future. And so here's my last slide. No, it's the second to last slide. What we're thinking of now is we're thinking of how to make a better detector. And here then is, this is now, you're familiar with this curve. This is the curve I want to use. And this is now the noise curve for advanced detectors. We are already, and this made the initial detection. We are right now working on improvements in that detector, which bring this down another factor of about 2. And then here is a detector we call Cosmic Explorer, or in Europe, they call Einstein telescope. This is a very much improved 3rd generation detector. And with those detectors, here is a picture of how far you will look. And what you can see, these colors match the colors in here. This is the collection of black holes, all these dots we think and our first detections are in 03, are ones that we've made, the ones that we are now, there's about 100 in here. There are many, many, many more black holes. And you get out to the blue one, you then get many more, look at all of the additional black holes. What you get, here's the same thing for neutron stars. And the further out you look, you get more and more of them until you get out far enough for these detectors, for these two on the bottom. And then you have encompassed all the population of the black holes and all the population of the neutron stars that are in our universe, out to the point where the very first stars are made at a Z of between 10 to 20 or 30. So that's the future. The future is to take this field into what I would call cosmology. And there are even ideas of how cosmology may have something to do with initial conditions in the universe where there were gravitational waves that came from the initial explosion. A very good Soviet and Russian, I think Ukrainian as well, Starobinsky physicist. He was a guy, a part of Zeldovich's group in Moscow, have calculated what might be the gravitational waves from an initial explosion and saw that it's very, very difficult to detect, but possible. And here now is my final slide. And this is what you can expect in the future. And I won't go into any more to say, this is frequency down here, this is strain over here. And these are different projects. And I'll just point them out because I've gone over time. This is LIGO and things that follow LIGO, up at the 10 kilohertz down to about 100 hertz, down to about 10 hertz. There is a space interferometer that's going to fly in the 30s, in 10, 20, 30s. That's called LISA. That was started in the United States, is now being carried on by the Europeans, and that will measure lower frequency gravitational waves. And they'll be extremely interesting. You'll see massive black holes colliding. There is a project which has been running for a very long time, looking at pulsars in our own galaxy and how their pulsing rate is changed by gravitational waves that go through our galaxy. They haven't really discovered anything yet. They think they see something, but they need years and years to prove it. And finally, there's an experiment going on in the Chilean Atacama Desert, as well as in the South Pole, which thought they had measured the cosmic background radiation, the electromagnetic radiation. The polarization of that radiation carries information about the primordial gravitational waves. They're called B modes, and that is one of the most exciting experiments going on right now. And they hope within the next 10 years that they may either say there are no gravitational waves at a level that are a certain value, or they have detected these gravitational waves that come from the moment that the explosion of the universe started. Thank you very much.
Thank you very much for a great lecture. Now we are going to our question and answer session. We have some questions from our participants. The first one is, how do you think, for how long laser interferometer gravitational wave observatory will be still useful for science?
Well, sorry, I'm about to cough. Let me take this off. Well, that's what I spent the last minutes of my talk about. I think it's more than, it's a new field, a completely new field. It looks at the universe where there are accelerating masses, not accelerating charges. It already has uncovered with something we never have seen with electromagnetic waves, namely the binary coalescence of black holes. It's seen the actual collision of neutron stars. So, no, it's well on its way of not only having shown important stuff now, but demonstrating its potential. I think it will tell us enormous amounts about the universe, things we have not seen because we have never been sensitive to this kind of measurement. So and a lot of people feel that way, that this is a new field which will add its own piece to the understanding of the universe.
Okay, thank you. The next one, what was the origin of the signal in the Weber experiments?
In the Weber, I wish I knew. I had at the time, I had some students. I have a theory, but I was never able to get Weber to agree. I'm old enough to know Weber. I'm 90 years old. And the Weber is dead, but I knew him as a young man. I knew him pretty well. And he was very skeptical of what I told him, but let me tell you what I thought it was. The Weber bars were made out of a very good conductor, aluminum. And I set up a little experiment of my own, and I have a house in the suburb of Boston. I set up a coil, a big, maybe 1 meter diameter, maybe 2 meter diameter coil. Wound the coil, put recorders on it, and could see about a milligauss if it lasted for a millisecond. And that's about what would have excited his bar. The pressure, the magnetic pressure of a good conductor like aluminum being squeezed by a time varying magnetic field, being squeezed by that is about right. And I saw typically a couple of events per day. And then because it was so interesting, I put one of my coils in the place where in Chicago, that city in the middle of the United States, where Weber had his detectors. We never did a coincidence experiment, but I gave him the data that we had of the 2 or 3 events a day that we had, and he was seeing 2 or 3 events a day also. And he just said to me, "Don't you think we're not? The way he answered me was, "You're so skeptical of us. We're not that stupid to be sensitive to gravitation, to magnetic fields. Have you?" And I then asked him, "Have you proved it?" And he didn't answer me. Okay.
Okay, thank you. Do you keep in some way work on LIGO project, on advanced LIGO Plus, or on developing laser interferometric technique? Yes, can you tell us a bit about your work?
Oh, my work. Oh, I've been deeply involved in all of it.
I mean, right now you're working.
Oh, right now, yeah, no, we have had a COVID has stopped me from going to the sites, but I've not done much data analysis. I did a lot of commissioning of all the detectors. That commissioning is when you go to the site, you carefully look at the data, and you then say there's something wrong here. You measure it, and you kind of try to predict what it is. I did an awful lot of that in the beginning. And now what I'm working on is the noise that might be dominant in a 40-kilometer system. I'm working very hard on the 2 things: how to make a vacuum system that for a 40-kilometer system cheaper, so it doesn't cost so much that you can't afford it. I mean, 40 kilometers of vacuum tubing at 10 to the minus 10 torr is a very expensive proposition if you just do it blindly. But there are ideas that you can make to make it cheaper. I think I can save several $100 million by making a system with ordinary steel rather than stainless steel. And I'm also working on the noise of that detector, but it's all theoretical and computational.
Okay, thank you. Next one is, does weather affect resultant or detector? And if yes, how can this problem will be solved?
Wait a minute, I missed the beginning. Does what affect the detector?
Affect results of detector.
I still don't understand. Say it again, please.
Does the weather affect?
The weather, you mean wind?
Yep.
Wind and sun, no, it doesn't. Yeah, look, it affects it a little bit at Hanford. It depends on how you do it. It turns out that we have, we wouldn't believe anything unless we also were measuring the environment at the same time. So when we built LIGO, and everybody who has done everything else has the same thing. You have seismometers, wind meters, anemometers, tilt meters, microphones. I mean, every conceivable thing you can measure in the environment, you measure that and could record that simultaneously with the gravitational wave signal, as well as 10,000 other signals that are in the instrument itself. And if you find that these signals that you're measuring, either in the environment or in the instruments itself, that are coincident with the gravitational wave, we veto those. We veto the gravitational wave that way. So we do an awful lot of what I would call side measurements to try to reduce the noise in the gravitational wave measurement. Now, I know the weather affects us in the following way. In Louisiana, which is the southern part of the United States, and this will be true wherever you are in the world, when there are storms in the ocean, the microcysm, which is a motion of the Earth between about 1/10 of a hertz up to about 1 hertz, it gets enormously excited. It's called the microcysm. And that's all due to waves in the oceans, especially when they hit solid things like the coasts and islands and everywhere. So that we can see that, and it causes us to have to increase the force that we hold the mirrors with. The way we measure the motion of the mirrors is we don't let them move. What we do, and this is, we measure the motion by actually putting them in a servo system, in a feedback system, so that they stay absolutely fixed with respect to everything else. And we measure the control signal that it is required to hold it in that fixed position. That is a very elegant way of controlling a lot of the noise. You can measure the noise and damp that way simultaneously. So, we are less sensitive in the southern detector when there are big storms on the ocean. And in the Pacific Northwest, we're sensitive to high winds that come from the ocean also there. And again, what that does is it doesn't cause us to get fake detections. It just compromises the sensitivity.
Okay, thank you. The next one, it is known that if a distant observer watches something falling into a black hole, then the duration time of this free fall to the horizon will be very big. But why do we see the merging of two black holes, which takes a very short amount of time?
Well, that's not true. They don't take a short time. That's a tricky time. First of all, we don't see the actual collapse. That picture you saw that I showed you of the collapse was a computer picture of the solutions of the Einstein equations. I didn't explain the waveform to you, but that waveform you saw is now much better understood than when we first published the initial paper. What we see now is, the question really comes down to, why do we see anything at all? Why doesn't it all fall into the black hole? That's one question that's related to the answer I'm about to give. And it turns out that near the event horizon, as before you get to the event, as long as the two black holes are still separated and their event horizons are separated, there is much of the radiation gets swallowed by the black hole, but most of it gets emitted into the vacuum. But when they get close to the point where the black hole forms and a new event horizon forms, something very interesting happens. The radiation begins to fall into the black hole, and we don't see that part. But we do see the part that is still emitted. And the part that's still emitted is part of motion of the black hole as it falls in, but is also partly the space itself oscillating in its normal modes. The space, the vacuum, has normal modes in Einstein's theory. And those normal modes were actually the first thing that was discovered theoretically. And we have now begun to see those normal modes. So that signal, which I didn't describe to you, at the very end of the black hole, just before the black holes completely go dead and you don't see them anymore, that signal is a mixture of two signals. The part that didn't fall into the black hole at the moment when the event horizons are merging, and also the oscillations of the metric in the metric that are outside of the black hole, but very close to the event horizon. So that tells you why you still see something, okay? And the time you see nothing about what goes on in the black hole. I have no idea how long it really takes. I don't think it's milliseconds, by the way, because the solutions are inside. By the way, it's not an easy solution. The internal Kerr solutions, these are the Kerr metric solutions, they are no longer orthogonal in time. Time becomes mixed in with space. So it depends where you are, how long a thing takes.
Thank you. And the next question is, do you expect discovery of a particle of gravity in near future?
That's a good question. A lot of people are worried about that. I don't think we're going to see it. I mean, this is a big issue, and it relates to whether we'll ever get a really interesting and worthwhile theory of quantum gravity, which is a very hot topic all over the world. I guarantee you that's a hot topic with some of the people who are listening. And certainly people in Moscow, they have been worrying about this even longer than many of the people in the United States. I'll give you some simple reasoning which doesn't work. If the gravitational wave frequencies were much higher, right now the highest we expect ever to see, our detector goes up to about 3 kilohertz. We could make high frequency detectors, but they'd be less sensitive. Then you can say there's more energy per graviton. And still, it turns out the energy per graviton is tiny. It's 10 to the minus 8, 10 to the minus 7 electron volts. It's tiny. So, you have to just take h nu divided by, h nu divided, well, you want to take the energy of the graviton is h nu. Now you want to divide that by into an electron volt. And I think I don't know, you get the number, it's probably around 10 to the 8, 10 to the minus 8, 10 to the minus 7 for the ones we've been seeing mostly. And there are just too many gravitons for the energy. And look at the energy we're talking about. An unbelievable amount of energy that we get to see a tiny amount of motion. Even that's why I showed you the thing where if you had put the pair of black holes at the position of the sun, you're still dealing with this incredible amount of energy. So I don't think we're going to see an individual quantum in any of the detectors that we have made. It's just, it's too smooth. You're dealing with 10 to the 30 gravitons. The square root of that is 10 to the 15. You have to look with a part in 10 to the 15. So that I think it's out of the question, I think. And unless there's some new source which really has very high frequency gravitational waves and we detected them. More likely, it's going to be, I think, if we ever see the gravitational radiation that is, now these are speculative answers. If we ever see the gravitational radiation that comes from inflation, which is the B modes, and you can do an experiment, but we're not working on it right now, to measure the B modes with actual detectors, not by inference using the electromagnetic field, the polarization of the cosmic background. That's a mission that people call, you can look it up on the web, it's called Big Bang Observer. People have thought about it. It's using LIGO-based technology with megawatts in the arms, high power lasers, interferometry with all these servo loops in space with distances that are commensurate with planetary distances. And then you can probably see, and you have to make, like Lisa has, you can make a upper limit, you can get an upper limit, but you might even get a detection of what's called the inflaton. And from that, once you know that, you can make an inference, because very few of these. you can get an idea of what must be the thing that makes the fluctuations of the density, the quantum fluctuations in the density. Those quantum fluctuations are made by the inflaton field, and those are the generators of the graviton. It might be possible by looking at the energy states, the spectrum of the primordial gravitational radiation, you might be able to get theoretically the idea of how big is a graviton for them. The other place, that's one, it's very theoretical and quite, the other possibility might be that if there's something different about the event horizon in a black hole when we get much better signal noise than we now have. I mean, we're going to have much better signal noise in these 40-kilometer detectors by factors of thousands than we have now. And we might be able to see some structure at the event horizon, which is derived from quantum fluctuations at the horizon. But I don't think we will ever see an individual graviton.
Okay, thank you. The question from Yuri is, dear professor, what kind of information about the epoch before the Big Bang could be obtained from the gravitational astronomy?
Yeah, well, that's what I've just been talking about.
Yeah.
I think that, to me, that's the most exciting prospect of the whole thing, but nobody will tell you how long it will take to make a detector. In other words, I think the most interesting thing that we did in cosmology is discover the cosmic background radiation, the 3 Kelvin radiation. That's completely changed the way we look at cosmology. The thing that would change cosmology here, there are some interesting questions even now. For example, is any component of the dark matter black holes, for example? We already know that it all cannot be made out of black holes. There are very good reasons why it can't. But for example, are there any primordial black holes? Now, we will know this a little bit from James Webb. You know, that's looking at the very first stars. And there shouldn't be any black holes if the stars are the only progenitors of black holes. That's what we believe right now. But you can make black holes out of pure energy. And maybe nature found a way to do that. And that'll be very interesting. Are there black holes in the primordial soup? And maybe there are some left over from the time before the first stars were made. That would be absolutely fascinating. And we can probably tell that also from any primordial gravitational waves. To me, those questions and questions of, are there modes of are the Einstein field equations still good at these incredible energies, where you're now talking about inflaton fields that come from inflation, and that the whole idea of generating gravitational waves from the fluctuations, the quantum fluctuations, which is the calculation that Starobinsky made. That would be also absolutely, you know, we have earth-shaking pieces of science coming out of this, usually because you have made a gravitational wave detection of primordial gravitational waves. So I don't hold that out for the things that's going to happen in the next 10 years. What might happen in the next 10 years is we'll find new sources of gravitational waves you've never seen before, probably. We'll probably find that we'll answer the question of where the black holes come from, which if we see that they're primordial, that would be spectacular. And we will also test Einstein's equations to an unbelievable sensitivity. But I think the most interesting thing that will happen is if, for example, the people who do the B modes see something, and that will prompt people to make a space-based gravitational wave detector that is sensitive enough to look at the primordial gravitational waves of the kind that Starobinsky has calculated. So to me, I won't be around. I mean, why should I? I mean, but even some of the people listening may not be around anymore when that finally works. But my God, what an interesting experiment.
Okay, thank you. And the last common little bit questions. What Nobel Prize meant for you? Can you tell us a little bit of your experience? Oh
dear, I was embarrassed a little. Why was I singled out of people of 1,000? I felt a little, yes, I did some thinking on this. It was awkward. I found it awkward. I was very pleased to get such a thing. I mean, my God, you know, you know, but I can only give it, I have to say it surprised, the way I look at it, It's not a prize for me so much as for a prize for all of us and the field. And I said that many, many, many times. It's awkward to think that. So I'm not that genius that everybody supposes a Nobel Prize winner to be. I'm an ordinary person. So I love to do experiment. I'm a better plumber than I am a theorist. Okay.
Okay, there are a lot of questions. One more about the topic. Do you think there is another universe? Was the universe before us? So that you have answered.
I don't want to go into that. That I know it's being asked. I don't have an opinion. I'll tell you why I have a trouble with that question. I don't know a way of finding out.
Right.
Yeah.
Okay. Thank you very much for a great lecture. That was a great time to talk with you. I wish you the best.
Well, I wish you all the best. I hope it all gets quickly better for you guys. Yeah. Okay.
Yeah, I hope very soon it will be safe and you can give and make a in-person lecture.
Well, that's something else. Okay. Thank you very much for having me. And it was good to talk to you. Bye-bye.